larger frequency, even large, and so on. So as you include more and more terms, there will be larger and larger frequencies. And as you include larger and larger frequencies, these errors are going to become smaller and smaller, but still there will be some kind of overshoot at the jump discontinuity, right? So that is something which is known as Gibbs phenomena. Okay, it's called Gibbs phenomena. Okay, and this becomes an important consideration, but we'll not go into detail of that. It's just for the sake of general knowledge that you should know. Okay, so but you should understand, what I want you to understand is why this is happening. This is happening because there is a finitely fast changing value of the function at that particular point. Okay, therefore there's a therefore unless you include very high frequency terms, you're going to get a large error at those values and those jump discontinuities. And as you are away from those jump discontinuities, you are actually, the function is continuous. Okay, so variation with x is not will not be as fast, so therefore error will be smaller. Okay, so anyway, I'm going to state that much about this, because even I'm not an expert in this. Okay, but that is something that you might have noticed. Okay, all right, now okay, now what I want to talk about is, so okay, so now if you recall, we had talked about the Fourier series for a particular kind of function which had we started with the discussion that a function f of x has a periodicity of 2 pi, right? So we started started considering functions with period 2 pi, right? That is how you get cos mx and sin nx, right? So period of a periodicity of 2 pi, right? But that need not be the case. Some like why should you constrain yourself to period 2 pi? The period can, in general, signals can have different kinds of periods, right? You can, why do you want to constrain it to 2 pi? But then the thing is, if you have an arbitrary period, so let's say for ft, say I have a period of 2L. Okay, then actually this can be exactly mapped with this, whatever discussion we have undertaken over here with the period 2 pi. All you need to do is just rescale your x for t. Let me call it t or x, whatever it does not. Let's call it t. Okay, this would mean that f of t plus 2L is equal to f of t for all t. Okay. So this is my defining property of the periodic function that tells me that period is 2L. Okay, and I have talked here, we had talked about a particular function which had period of 2 pi. Okay, and these were expanded as sin mx and cos mx, these kind of basis functions, right? So what kind of modification would you need to do if the period was not 2 pi but some other number? Okay, well, all you need to do is just this independent variable, this t, or here it is x, so here it is t. All you need to do is just stretch or compress this variable so that the function, so that the length 2L becomes equal to 2 pi. That's all. Okay, so you have to do stretching transformation, stretch or compress, basically scaling. This is called scaling transformation. Okay, compress the t-axis so that 2L becomes equal to 2 pi. Okay. All you can do that, right? So for example, if you have a function which may be it may look like this. Okay, something like this. Okay, suppose this is a function with periodic and the period is 2L. Okay, so this is my t-axis, this is my f of t-axis, f of t. Okay, and then I can take up this axis, and I can, and suppose this length is, this is 2L length, and say this much is 2 pi. Okay, all I can do is I can just, about the origin, I can stretch this thing. Okay, so that this 2L becomes equal to 2 pi. Okay, so I can just, it's a redefining a new variable. Okay, so that that new variable is defined in a certain manner, so that 2L is a linear transformation, so that 2L becomes equal to 2 pi. So what do you do? How do you define that? Well, you can say that if you define t equals to lx by 2, lx by pi, okay? So when x is equal to 2 pi, t becomes equal to 2l, right? So that when x equal to 2 pi becomes 2l, okay? But when t equal to 2l, x becomes equal to 2 pi, right? So this is the kind of rescaling I have to do. So you have to define a new variable x, which is pi t by l. Okay, x equal to pi t by l. So if I know pi t by capital, so if I know t, I can find x. Okay. So that this is my new variable that we have defined. That's all. So this is substitution, new substitution of. Okay. All right. So if this is the case, then you can see that f of t plus 2l would be equal to f of t is equal to lx by 2 pi. Okay. So lx by pi plus 2l. Okay, and this I can write down as f of L by pi. I can take outside x plus 2 pi. Okay, and if I define a new, so basically if after this substitution, okay, so here what it would mean that f of t would be, if I replace t with f of lx by pi, that would be, let's call it a capital F of x. So it's a new function of x after the substitution. Okay, so it's capital F of x. Then Lx by pi. So this would mean that basically this is equal to capital F of x plus 2. Okay, so f of t, which is capital F of x. Okay, so that would mean that basically this becomes a period. Basically becomes a period of so f of t. To start with f of t equals to, maybe I can start by further saying that capital F of x, which is small f of t. Now f of t is period 2l. Okay, so capital F of x is equal to f of t. That is equal to this one. This is equal to this. This is equal to this. Okay, and this is equal to this. So you have gotten f of x equal to f of x plus theta. So basically, this function now is periodic with period 2l. Now I can, whatever we had talked about for a function here, everything that is applicable to this function is applicable to this function. Okay, so now this f of x can be written as sine mx and cos mx in terms of sine mx and cos mx, right? So if you do that, that would mean that so therefore basically I can write down f of x as a periodicity of 2 pi, where we know that small f of t has a period of 2l. So we've just mapped out a new function, that's it, with a desirable property. So you can write down f of x would be equal to a0 by 2 plus an cos nx plus bn sine nx. Okay, summed over n from okay, so summed over n basically. Okay, and this I can write down. Therefore, f of t can be written as a0 by 2 plus now an, and now I have to write down in terms of t. X was equal to t pi t by l, so that would be cos of n pi t by l plus bn sine n pi t by l. Okay, so this is your form. If you don't have a periodicity of 2 pi, then that's a modification you need to do. It's not just nx, cos nx and sin nx. It becomes n pi by l into t, and so rather than writing just cos nt and sin nt, you have to write n pi by l into t. That's all. So this is the Fourier series for arbitrary periodicity of 2l. Okay, and you can find out an and bn. We have already shown that to be 1 by pi, that becomes 1 by. So remember, according to here, your an is what? An would be equal to 1 over pi integral f of x into cos nx dx, okay, minus pi to pi, right? This is how you found out an and bn, right? 1 over pi f of x cos sine sine nx dx minus pi to pi. Okay. So now if I redefine a variable in terms of t now, so t was so x is equal to pi t by l. Right? So dx will be equal to pi over l into dt. Okay. And that's it. So therefore, if I have to write down everything in terms of an and bn in terms of t variable, that would go as an will be equal to, if I just write down from here, okay, an would be equal to 1 over pi. An will be equal to 1 over pi integral. So now when x is pi minus pi, t would be equal to minus l. Right? So that would be x equal to minus pi, t would be equal to minus l. That would go from minus l. When x equal to pi, that's upper limit, then t would be equal to l. Okay. That would be l. And f of x is the small f of t. Cos nx would be cos n pi t by l. Okay. And dx would be equal to pi by l dt. Okay. So these pi cancel out, and what you get is an should be equal to 1 by l. This l I can take outside. Okay, so 1 by l integral minus l to l f of t cos n pi t by l dt, and dn would be equal to 1 by l. Similarly, we can show that simply f of t sin n pi t. These would be the working formula for finding out these coefficients an and bn if you are writing in terms of t function, right? So where the periodicity is L, okay, the an and b, so f, so the general rule is that if you have a periodicity function f of small f of t with period 2L, then ft can be expanded in this form, which is written up here. Okay, it's not just cos nt and sin nt, like you had cos nx and f if the period was 2 pi, but here just is little bit modified. Here is a coefficient of n pi by l associated here, right? So that's all you need to do. And accordingly, an and bn values are related to f of t by these formulas. Okay, so that is the modification we need to do. Okay, all right. Now, so you can see that basically, what is the period of each? Just a second. Hello, I have a class going on. Okay, so all right. So now, okay, so now each basis function. So your basis functions are cos n pi t by l and sine n pi t by l. Okay, so these are my basis functions now with your period of 2L, right? Then what is the periodicity of these? Okay, periodicity is, well, you all know that basically that would be equal to 2 pi over n pi by L. Okay, that would be equal to 2L by n. Okay, so it's the same thing which I told you earlier. If the periodicity is 2L, then this would mean that period basic fundamental period is 2L by n, which would mean that each basis function will oscillate n times. Okay, so if you take n equal to 1, the period is 2L, so it will oscillate once. If period is n, if you take n equal to 2, the period is L. So that would mean that over L it oscillates once. So over 2L it will oscillate twice. Similarly, if the period, so for any value of n, so this will this oscillates n times, okay, over the length or time, whatever, can be x or t. This t is just a variable. It can be time, can correspond to time, it can correspond to length, whatever variable is there, n times. Okay. So basically, you can say that the periodicity is Tn, nth basis function has time period of 2L by n. Okay, and therefore frequency would be frequency is 1 over t, right? This is 1 over t, number of complete oscillations done over a length, unit length, right? That would be 1 over t would be equal to n over 2L. I'm going to call that mu n. Okay? So this would be the frequency of nth basis function, with a cos or sine, right? Okay, so therefore it basically tells me that there is a so when you write down a function f of t equal to a0 by 2 plus an cos n pi t by l, okay, and plus bn sine n pi t by l. Okay, so this is has a frequency nu n. Okay, and this particular component has an amplitude of an. Okay, so you can say that every frequency has some amplitude. Every frequency signal has some kind of amplitude associated with it, and that is what is referred to as frequency spectrum. Okay, that's frequency spectrum. Okay, so every frequency signal or frequency component, this frequency component, it tells me that the spectrum tells me that particular frequency will have how much, particular frequency component will have how much strength, okay, how much contribution to the net signal. Okay, so that is frequency. Every frequency component will have some contribution to the net signal, to the net function. Okay, so that information is actually called, referred to as frequency spectrum. Okay, all right. Now, okay, now we are still limited to a very particular kind of function, which we do find its application, but still a very restricted class of function which are periodic. Okay, so we have basically learned about how to decompose a periodic function with any arbitrary period in terms of sine and cosine functions. Okay, that was the formula given in the last page, right? Now, if the function is not periodic? Okay, so if the function is not periodic, so how? So is all this discussion of any use to those kind of function which are not periodic? Can we write those kind of functions which are not periodic also in terms of sine and cosine functions? Actually, the answer is yes. Okay, so what kind of modification needed for non-periodic function? Okay, so what do you do? Well, basically a non-periodic function, you just identify this to be like a periodic function. Amit, I'm unable to understand how n is affecting the frequency. Well, okay, so let me answer your first question, which is if you increase n, right? So say t is the time domain, t is a time variable, okay, and say its period is 2l, this length is 2l, okay. My original function has periodicity of 2l. Now my basis function, so nth basis function will oscillate n times here. So we have already talked about that, I guess. So this is n equal to 4. Okay. If you increase n, it will oscillate more faster, right? So if I say if I have n equal to 6, it's going to oscillate 6 times between the same length, right? Therefore, the frequency will increase. If this is a length variable, if this is x, if e is a length variable, then this becomes wavelength. Okay, then your wavelength will decrease. Okay, or wave vector will increase as you increase n. Okay, so inverse of wavelength will increase. Is that all right, Amit? How n is affecting? Okay, and also more the value of n, flatter will be the curve, but more is the frequency. What does that mean? More the value of n, flatter will be the curve. Why? I don't think it's just opposite. If n is larger, your if your n is larger, the corresponding basis function is swinging fast. Okay, so this would be like extreme, very high n value would look like this, something like this. Okay, so plotting on MATLAB for Fourier curve. I don't understand what the question is. I'm unable to understand your question. Plotting on MATLAB for Fourier curve. What does that mean? Uh, why do you say flatter will be the curve, but more is the frequency? I mean, I'm unable to understand your question. Maybe square section. Okay. So you are referring to the square wave that we talked about. All right. So yeah. So square wave case we just talked about. Okay. Here, what I said is that your error will be larger if you do not include more and more terms. Okay, so basically if you go to higher, unless you have higher frequency components included, you will not be able to capture this sudden change. So for example, you might have noticed, well, maybe I can probably draw it over here. Yeah. So you might, though if you've done the plotting, you might have noticed this. So for example, let's say this is my minus k to plus k, and it goes up to here, and then suddenly there's a change over here. Right? You might have noticed that for smaller value, if you have, let's say, 5 terms included, okay, if you have included 5 terms only, that means you are basically ignoring higher frequency components. Your curve might look like probably this way. At this point, it's going to look like this. Okay, if you have a smaller n, let's say, if you increase the n value, okay, higher n, it might look like probably, if you increase n value, it's going to look like this at this boundary. And if you increase further more n, if you include more terms, okay, you might look like this. Okay, something like that. Okay, so this basically this trend of sudden change is better captured if you include more and more terms, because you have to have, in order to include this, in order to have this effect, this sudden change in your function, that implies basically presence of higher frequency, right? Because it's a very fast change. That means there is a significant contribution by high frequency components which we are ignoring if you are ignoring those components. So if you include them, your this approximation becomes better and better. This sudden upturn, okay, this discontinuity is approached more and more as we include more and more terms. So I guess that would be my answer. I hope this is what you were asking about. It's still not clear. Okay, all right, so fine. All right, so here I would say that n1. So I can say this is basically the black curve is N1, this N1 terms, the red curve is N2 terms, the green curve would be N3 terms, where N3 is larger than N2 larger than N1. Okay. That is the trend that you should notice. Okay, N3 is larger than N2, and that would be larger than N1. Okay, so more and more terms include, you are actually able to capture this discontinuity bet in a better fashion. Okay, gotcha. Okay, all right. So any other doubts? So these are some very important insights you need to know. Okay, I'm not going to mathematical derivations or details of those things, any quantification, etc. But some qualitative aspects that you should be aware of in these Fourier series discussion. All right. Okay. Now, what was it talking about? Yeah. So, what kind of modification is needed for non-periodic? Well, non-periodic function is essentially a periodic function with infinite periodicity. Okay, with infinite periodicity. Okay, all you need to do is whatever discussion we have carried out, we can look at that in a limiting scenario where frequency tends to infinity. Okay, so sorry, period tends to infinity. Okay, so when period tends to infinity or frequency tending to zero. Okay. So what happens there? Okay, so let's talk about that. Now you have seen that. So let's say I have a periodicity of 2L. Okay, so FT. Let me write down. Let's forget about for now. Let's forget about the DC offset part. Okay, 0/2 I'm going to ignore right now because that's not very interesting. This is the average value, which I'm going to subtract from the FT and get a function which has average value to be 0. Okay, so this would be an cos n pi by L T plus En sin n pi by L. Okay. Well, actually, it's there. If you have 0 term, it's there already. Fine. So this is a general form. I'm not actually studying it. Okay. And I have a0 to be equal to 1 by 2p. This is average value, FTDT minus L2L, and PP over PL, and LPL, L2L, and AN 1 by L times L2L, FT cos n pi p by L, and F 1 by L, L2L, P and n pi p by L. This is what we have learned. Okay. All right. So when you let so what you want to do is actually, now I want to let this L tend to infinity. Okay. So as you let the L tend to infinity, okay. So as we let the L tend to infinity, okay, what's going to happen? Well, you can see that every component, so you can basically enumerate, right? You can enumerate different components. Okay, the first one, second one, third one, fourth one, etc. And each you can give a numerical label to each of them, right? Sin mx, m is 1, m is 2, cos mx, sin mx is m equal to 1, 2, 3, etc. Okay, you can label them, and for each such label there is a frequency that is given by n by 2. Right? We have seen that. Okay. All right. So as L increases, okay, what's going to happen to mu n values? It's going to go down, right? Well, if you look at mu n plus 1 minus mu n, okay, the difference between the frequencies of two consecutive basis functions, okay, the first one, second one, or second, third, fourth, so on. that would go as n plus 1 by 2l minus n by 2l. That is equal to 1 by 2l, right? So difference in frequency between two consecutive uh, consecutive basis functions actually goes down as L increases. Okay, the difference between two consecutive between the frequency of the two between the frequencies of two consecutive basis functions goes down as L increases and will tend to actually zero when L goes to infinity. Okay? Tends to zero as L goes to infinity. Okay. Okay. So what does that mean? So you can see that now, if your L is finite, okay, I have I have nu n labeled by, you can say that this is first frequency, which is 1 by L, 2L. Second, so you can say that nu1 is 1 by 2L, nu2 is 2 by 2L. So each is a discrete frequency, okay? Each signal will be having basically spread discretely, okay? But when L goes to infinity, they will be actually, this becomes, nu becomes a continuous variable now, because difference between two consecutive value of nu's becomes zero. Okay, that tends to zero. Okay, as L goes to infinity. Okay, so basically you can show it like pictorially. You have for finite periodic signal. Okay, you will have u1. You'll be having some a1, a2, whatever. This is the frequency spectrum that might look like this. Okay. So these, maybe you can say these are the values of an and u. Okay, so this would be 1 and equal to 1, 2, 3, 4, 5, 6, and so on. And each component will be having some an or bn. You can plot both an or bn. Okay, and they will be having some value. I have shown a positive. They can be positive or negative as well, but it will have some kind of this kind of this is also known as, we square them, it's known as power spectrum. Okay, this kind of frequency spectrum you may get. Okay, now as this difference is 1 by 2l. This difference is 1 by 2. They're equally spaced because nu n plus 1 minus nu n is 1 by 2l. And now if I look at a function, what I'm going to do next is basically think of like uh, you can think of like function that looks like this. Let's say I have a function that looks like this is x, whatever you can call it, and let's say a function that looks like this. Okay, this is not particularly periodic. Okay, now what I can do is I can define a periodic function. So let's say I have defined this value, and then I can define a periodic function the same kind of shape. Okay, and then you can basically repeat it in space, right? And then you have certain periodicity, and then you let that periodicity go to infinity. Okay, so that way you are actually going to mimic a aperiodic function. But when you do that, what you're doing essentially is that you are actually bringing these frequency components closer and closer. Okay, so n equal to 1 and 2. If you increase L, these will probably look like this. Further reduce, then eventually in the limit when L goes to infinity, these new values, okay, which are discrete now for finite periodic functions, becomes continuous variable. Okay, so 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 basically your uh, in the limit the L goes to infinity, okay, or you're trying to basically um, looking at a general aperiodic function, not periodic, okay, your mu n, the delta nu n tends to 0, mu becomes a, continuous. Continuous. So now you don't talk in terms of new n's, okay, or new one, new two, but it's just a new value, okay. It becomes a continuous variable, okay. And therefore, well, I will not go into the rigorous derivation, but simply you can write down this as, if you look at f of t now, you have 1 by 2l of t dt, okay, minus l to l plus n equals to, let's say I have taken 0 component outside, so n equal to 1 to infinity an cos n pi t by l, so n pi t by l plus bn sine n pi t by l. Okay. So what was that? N by L was mu, right? N by 2L was mu. So let's call this 2 over here and 2 over here, multiply 2 over here, 2 over here. This I can write down as, this part I can write down as plus, this is so plus, and plus n equal to 1 to infinity n cos n by 2L is mu n, so 2 pi mu n into t plus bn sine 2 pi mu n into t. Okay. Okay. So you are summing these things. So for every n, there is an and bn, right? But in the limit when this goes to, when L tends to infinity, mu's become continuous variable, and accordingly anything that is labeled discretely, that becomes a discrete variable, becomes a continuous variable. So a, n and bn also become continuous variables, right? So basically what you're doing is, this is a sum of discrete variables, and then the limit when you take this when the difference, when you have, basically you are summing up these values. Suppose you are summing some function, and in the limit when they become very extremely close, okay, what does that become equal to? The summation is basically becomes equal, it becomes integral, right? These become integrals, okay. So this is represented by simply, uh, so in the limit, this, when the L tends to infinity, ft's can be written as an integrals, okay, and that would be basically, now, well, we can call, you all probably know that 2 pi nu is given in angular frequency, right? 2 pi nu is also known as omega. So cos omega nt and sin omega nt, you can write down like that. Okay? So this is given as, this is basically takes a form which is integrals. These become cos omega nt integral, and these coefficients become a functions of omega rather than being numerically labeled as a function of n. They become functions of omega. Okay? And I'm going to write capital A now, and cos omega nt dt plus d omega, that will go from omega goes from 0 to infinity, and this will go from 0 to infinity, d of omega sine omega nt. Okay. So uh, this is your representation of ft when it is not periodic. Okay, there is no L appearing anywhere here, right? So this is your when ft is not periodic, you have this kind of representation. You can still write down in terms of cos and sine functions, except that those cos and sine functions will not be labeled discretely. They will be actually, so you can think of like, if I have one cosine function like this, other cosine function might look like this. It is slightly deviated from my current value, and the next one can be slightly deviated. So all possible frequencies are allowed in my representation of a non-periodic signal. That's all. Okay. All possible omegas, omega is wrong. So this of omega t and sin omega t, right? So that is going to be the, this is called Fourier transform. Okay? this is called Fourier transform, not a series, but Fourier transform. So Fourier transform is used for representing a non-periodic function in terms of sine and cosine functions, right? Okay, and now we are still, so for example, in series, I had a way to find out ans and bns. Similarly, here in the Fourier transform, I have a way to find out a omega and b omega, and those are given by a omega is given by, you might have probably guessed it, so that would be 1 over pi, sorry, 1 over pi, right? Minus infinity to infinity, because remember in my original expression an was given by 1 by L minus L to L, okay, and that was Ft cos omega nt. So here it becomes simply Ft cos omega t dt. And d omega, I'm not going to derive this, just give it this formula. Okay. You must have probably seen the derivation. That's class. All right, so these are the Fourier transforms. Okay, so I can, so if you have any function given to me, okay, I I can ask the question like what, how much does a particular cos function or sine function with certain some value of omega, some arbitrary value of omega, contributes to this particular form of the function. Okay, so that can be obtained by doing this operation. Okay, so if you know f of t, and if you're able to evaluate these integrals, okay, then you will get the values of omega and omega. Okay, so that is my that is what is called Fourier transform. Okay, all right. So generally speaking, if the function has so suppose a function that may look like very gentle and not very highly oscillating. There is, the function is very, has a very gentle variation, something like this that I've shown up here. Okay, and you can contrast this with a function that might look like this. Okay, so if it has variations which, sorry, this is a pretty good way of showing a function, but let's say if I have some arbitrary function that might look like this. Okay, and if it has oscillations, okay, or a variation which is sharp somewhere, that would mean that it has, so for example here in this function, for large values of omega, a omega will be very small. Okay, larger frequency components will not contribute significantly to this function, but this will not be hold here. Okay, in this case you have larger frequency components in contributing more, much more as compared to this function. Okay, so larger frequency components will not contribute much to this function, but they will contribute to this function. Okay, so if you have sharp upturns and sharp turns, sharp changes, quick changes, faster variations in function, that would imply automatically, you can see by looking at this that okay, this function has, for example, let's say omega equals to some value which you can look at by that you can judge when you practice more. But generally speaking, large omega, a omega will be very small for this function, whereas this will not be. For this function, a omega will not, a and b omega may not be small. Okay, so that gives you a sense of looking at a function. It gives you a sense of what kind of omegas are relevant in my representation Fourier transform. Okay, all right. So this is what I wanted to discuss about Fourier transforms. And maybe I can do an example also. So one example. So let's say I have a function f of t which is equal to 1 if t is, so this is my square pulse, okay, 0 onwards. Okay. Now there are certain conditions that must be fulfilled for Fourier transform to exist for a given function. But we will not go into those things. All we need to know is that f of t should be it should be integrable. Basically, if it integrate it from minus infinity to infinity, it should not blow up. Okay, integral, it should be a finite strength function. Okay, meaning that its area under the curve should approach a limit. In the limit, if you include all the t from minus infinity to plus infinity, for example, if you have a curve that looks like this, it's linear, a line. Okay, if it's a line, okay, that extends from minus infinity to plus infinity, uh, well, or maybe, a good example. Let's say, yeah, maybe I can imagine. Let's say I have a parabola. Okay, so I have a parabola which is defined from minus infinity to plus infinity, right? So area under this curve, as you keep on going minus infinity to plus infinity, okay, it's going to blow up, right? More, if you go to infinity, the area will shoot up to infinity. Similarly here, okay, so total area will shoot up, will actually be not finite, the limit from minus infinity to plus infinity. But this, for example, okay, if you include more and more region, the area will converge to some constant value. Okay? Such kind of functions are good functions for Fourier transform representation. Okay? So we will not, we will not go into the details, but assume that function. So for example, this function that I just listed showed up here, this is like f equals to 1. So this is this function. Okay. So okay. So this would be this area. This net area is always finite, right? So if we include all the t-axis from minus infinity to plus infinity, area under the curve is finite, right? So this is good. Okay. So how do you find those Fourier transform? This a omega would be given by 1 over pi ft cos omega t dt. Okay, and that is minus infinity to plus infinity. Okay, and that will, so in this range it is already 0. So I can just bring this, make this integral from minus 1 to 1. Okay, and ft becomes 1 here into cos omega t dt. Okay, that turns out to be 2 sine omega by pi omega. I think that's correct. Let's check that. Okay, so that would be your a of omega. Okay, and b of omega would be 0 actually. If you just do this, 1 into sine omega t dt, sine is an odd function, so minus 1 to 1, that will be 0. Okay, that would be b omega will be 0. Okay, so generally every odd function will have b omega 0 and omega finite. A omega will be having some expression, and it tells me that you can see that the contribution of different frequency is given by this expression, meaning that if I plot a omega, okay, it's going to look like, how is it going to look like? Sine to some constant sine omega of omega, so it's going to look like this way. Okay, for very large omega, okay, there will be contribution will be less and less, but it will not be, never be 0. Okay, and if it's sine omega, it's going to, it would have looked like this. This would be the contribution. This would be a of omega, which is omega. Okay, so it tells me that these are at different omegas. A omega looks like this. So if you multiply with 1 by omega function looks like this. Which of infinity and goes to 0. Okay, so product of these two would look like this. Okay, so this is 1 by omega. This is sine omega, and this is sine omega. Okay, so that would be your a of omega. That's how it's going to look like. Okay, it gives you basically quantifies, it gives you quantifiable result, which is tells me that okay, a particular omega will have, naturally tells me that these omegas will have no contributions at all. These omegas, when omega equals to 2 pi, okay, there will be no contribution at all. Okay? So that is an important information. Okay, so these kind of information are useful when you further analyze this function or subject these functions to some, for example, they could be the homogeneous term appearing in a differential equation. Okay, so this information with this transform will be useful when you have to solve certain differential equations. All right. Okay, we'll come back to that. Any questions so far? Or we can continuous again. Rohan, what we can continuous? New? Do you still have a question, or do I still need to go back to the question, or is it sorted out for you? Done. Okay, good. That's good. I hope. Yeah, basically the frequencies become so cold that the distance between them is zero. It becomes continuous. That's it. Okay. Any more question? If not, then I'll stop the class and. Okay. All right. Bye. How we expect it? Rohan, AW, E omega and D omega. Okay, you didn't get it nice. Okay, let me explain that in next class. You can focus on it right now. We will talk about it. Okay? Please remind me about the question tomorrow. Okay? All right. Thank you.